All right, so I'm going to introduce another concept related to linear momentum. This is called angular momentum, right? It useful and important concept, but pretty straightforward, I think. So the angular momentum is given this symbol h, and we have to specify about the point that we're discussing. It's because it's somewhat arbitrary. All right, so the angular momentum is just the cross product of the position and the momentum vector. All right. So what I mean by that is, so just in 2 dimensions for ease, I'm going to show you a 3-dimensional case here in a second, but if we have some particle, and that particle is moving in this direction, say. So here's the position vector, here's the momentum vector, and so you can kind of tell this particle is going to be rotating clockwise. So by the right-hand rule, the angular momentum will be in the negative z direction. Okay, it'll be into the paper. So this was always a point of confusion for me, because I remember the right-hand rule, like if I remember the right-hand rule being in terms of the vectors. So just be careful about this. I'm hoping not to say this so I don't pass my confusion on to you, but when you're taking the cross product of 2 vectors, it is assumed that the tails are joined. So in this case, that would be R, and this would be L. So they both originate from, so now it makes sense, the cross product passing through R then to L, pointing down. All right, but it's typically drawn where we have the momentum or the velocity vector attached to the position. And so if you look at it here, you would, my mistake was always thinking that this was going to be a positive value. However, you can look at it and tell that this R vector will be rotating this way. So just be careful. However you need to think about it to be accurate, but you can either think of it as the right-hand rule traveling in the direction of rotation of the particle itself, or if you want to use what we defined as the cross product, then the right-hand rule passing through R to L is you'll get the right answer. Okay. So just like there's a thing called a moment of a force. So the moment of a force about O is just like the angular momentum, but for the force itself. And so this is equal to R cross F. All right, so if I had that same particle and had a force acting on it like that, then R cross F would be, in this case, still a negative value, but so this is the moment. You can think of torque or something like that. So if I have force acting at a distance, across a distance, this is generating a torque at the origin here, and the angular momentum is related to the torque in the same way that linear momentum was related to the force. And so this, just this statement allows you to write these two impulse equations. So we have like an angular impulse just like we had for linear impulse. And then just for completeness, so I have a 3D example of what this might look like. There's this pretty cool software called GeoGebra. I guess it's owned by Google now. It allows you to illustrate stuff like this. But what we have here is a particle P traveling along a path, and it has a velocity vector which is obviously tangent to the path, as well as the acceleration and stuff that keeps it confined to the path. All right. Now, the force is clearly going to be in the same direction, but and proportional to the acceleration. And in this case, I've set the mass to be 0.5. Now, the angular momentum is going to be perpendicular to both r. It's because it's r cross v, right? So it's going to be perpendicular to both the position vector and the velocity vector. Here, let's stop the animation. It's giving me issues. All right, here we go. So yeah, so here, if I line these up, you'll see that here's RV, and I'm looking straight down the angular momentum. So the angular momentum is perpendicular to both R and V, just as the cross product should be. All right, this curve down here, I have it illustrating the sort of like a this is not a physical thing. This is just the path that the tip of the angular momentum is taking, right? And to illustrate the fact that the moment, which is in this case, the moment should always be perpendicular to both R and F, which is the case here. Okay. The moment generated by the force is perpendicular to both the force and the position vector. And if you notice, it is also at the point of it also shows the rate of change of the angular momentum. You can tell that the angular momentum is changing along this path here, and so the moment is going to always be parallel to the path at the point where the angular momentum is tracing it out. See what I'm saying? So right here, the moment is parallel to this path because it is describing the rate of change of angular momentum. That's kind of the point. All right. So I'll put a link to this, and you guys, this is actually kind of a neat little program you guys can play with. It helps describe topics like this, and it's pretty cool. It's a little for me, it was a little confusing to get it to do what I wanted to do because I'm used to working with like MATLAB and stuff like that. But the syntax and stuff is a little different, but it's pretty powerful. And I'll put a link to this in the description if you want to take a look at it in 3D. All right. So the idea was that you can see the relationship between the moment generated by the force and the angular momentum generated by the force. And so you can see that Angular momentum is a vector, so it'll be added vectorially, and its orientation, magnitude, and everything.